let's look at systems of ODE. And let's try to connect systems of ODEs to nth order ODEs that we just talked about. So let's look at an example. We have y second plus cos t y prime minus 7y equals to 0. And this is a perfectly legit linear second order ODE. So we could look at it from the point of view of we can just solve it with the techniques we have developed until now. But we can look at it in a different way. We introduce a new function, a function x function of t, and we define it to be the first derivative of y. Then the second derivative of y is equal to the first derivative of x. And we can write x prime plus cos tx minus 7y equal to 0, combined with the information we just introduced that x is equal to y prime. When we write systems, it's usually normal to write the first derivatives all on one side and all the rest on the other. So we rewrite this as x prime equals something that depends on x, y, and t. And y prime equals to something. That in this case is very simple. Y prime is equal to x. So we have turned a second order ODE into a system of two first order ODEs. It turns out we can do this in general. We can take an nth order ODE in the form y at the nth equals a function of t, y, y prime down to the n minus first derivative. We're not requiring f to be linear in this case, and we can rewrite it as an nth order ODE. We have an nth order ODE and we want to rewrite it as an n-dimensional system of ODEs. So we introduce x1 and we place it equal to y. We say x2 is y prime, x3 is y second, down to x to the power xn, so the nth index of x, is equal to n minus first derivative of y. Then xn prime satisfies the ODE xn prime equals f, the same f as we had before, t, and now we replace all the y's by the appropriate x. So ft, x1, x2, x3, down to xn. On top of this, we need to remember the information we introduced. So we have introduced that the first derivative of x1 is x2, and the first derivative of x2 is x3, down all the way. And this is a system of ODEs. We have to solve it all together for it to make sense. In even more generality, we can have a system of ODEs of the form x1 prime equals f1 of t, x1, x2 down to xn, x2 prime equals f2, t, x1, x2, and so on, and all the way down to xn prime equals fn, t, x1, x2 down to xn. Why do the f's have indices? Because we're saying that they have so much flexibility in there that we can use anything in those positions. Any line can have a different right-hand side. And here, a solution of this whole thing is a list of functions. So we don't have one solution anymore, we have n different solutions. Well, one solution has n parts. We have a solution for x1, for x2, for xn, and you need all of them to make a solution of the whole ODE system. Let's look at an example. We have this fourth derivative of y equals y second times y prime minus y sine of t y second. So we introduce x1 equals to y, x2 equals to y prime, x3 equals to y second, x4 equals y to the third. We don't introduce anything for the fourth derivative, because the fourth derivative will be replaced by x4 prime. And this is what we do. We replace the fourth derivative by x4 prime. Everything in that equation we replace with the corresponding appropriate value of x. So x to the third is replacing y second, x2 is replacing y prime, x1 is replacing y, and sine tx3 is replacing sine t y prime, y second. But then we also have to have information about x3 prime, x2 prime, and x1 prime. So for every x that you introduce, you need a corresponding ODE. As for nth order ODEs, a first order system of n ODEs needs n initial conditions that we write as x1 t naught equals x1 0 down to xn t naught equals xn 0. And we have this theorem that corresponds to the existence and uniqueness theorem before, but in a more general setting, because we are expecting f's to be independent. So looking at the previous ODE, if we have f1, f2, and fn functions, such that all their cross derivatives with xy are xj are continuous, so we have partial derivative of fi over partial derivative partial of xy. I'm sorry. We take f1, f2, fn to be functions, and we want all the derivatives with respect to all x's to be continuous. So there is a small typo, there should be xj and not xi. So we want the partial derivative of xi with respect to xj to be continuous. And fi is f1, f2, f3, fn. And xj is x1, x2, x3, and so on. So we want all possible combinations of f's and x's to give us a continuous derivative. So in here, we both have a partial derivative of f1 with respect to x1, but also f1 with respect to x3. And we want them to be continuous, all of them, on a region R in the space t, x1, x2, x3 down to xn, such that we have a bound for t between alpha and beta, a bound for x1 between alpha 1 and beta 1, a bound for x2, and so forth. So we want a sort of a rectangle, but in very high dimensions. And we want the initial condition that we have imposed, so t0, x1 0, x2 0, and so forth, to be inside this region. Then, if we have continuity of f, if we have continuity of their derivatives, and if the initial condition is within the continuity region, then there is an interval for t going from t0 minus h to t0 plus h, in which there exists a unique solution. A solution that satisfies the initial conditions. Notice that when we have linearity, we can say that the solution exists for the whole interval in which we have continuity. But when we don't have linearity, we have the existence and uniqueness on some interval that we don't know. We just know that it exists an interval in which we have existence and uniqueness. So I just talked about linearity. What happens when the system is linear? How can it be? We call a system linear if f1 and f2 and so on are linear in x1, x2, and so on. What does it mean? It means that they have this specific form. So f1 has to have the form function of t times x1 plus function of t of x2 plus function of t times xn plus function of t. And in general, each of them has to have the same format. We have x2 prime equals function of t x1 plus function of t x2 plus so forth, plus function of t xn plus function of t. And this is just a formalization to give names to all these functions. And the g that we have introduced, g1, g2, and so on, are the non-homogeneous terms. If G1 is equal to G2 and all of them are equal to 0, then the system is called homogeneous, as we had in simpler cases. Theorem: if all the functions of time that I just introduced are continuous on an interval between alpha and beta, then there exists a unique solution that satisfies a given initial condition on t0 for any t0 in that interval and any combination of initial conditions real. The solution is unique, as we just said, and exists for all value of time in the interval. So this is the stretching to systems of the existence and uniqueness theorems that we have for linear ODEs already. If the situation is linear and your functions are continuous, all your functions are continuous on an interval, then you have existence and uniqueness on that interval. The only thing you need to be careful with is that your t0 must be in the interval. So between alpha and beta. You cannot be at the boundary of the interval. You cannot have t0 equal to alpha or equal to beta. If we write the ODE in this form, then we can rewrite it in a matrix form. So you know how you can multiply matrix and vectors? You can do the same when things are functions. So now we have a vector in which each element of the vector is a derivative of x. So we have x1 prime in the first element, x2 prime down to xn prime is equal to a big matrix in which all the p's are placed in the right position. So we have p11 in the first position, p12 in the first line second position, down to p1n in the first line nth position. And the same goes for p21, p22, p2n, pn1, pn2, pn. And this big matrix of functions depending on t gets multiplied by a vector of x1, x2, and so on. And if we are in the non-homogeneous case, you also have to add a vector with the non-homogeneous terms. This is to explain why we're going to spend some time soon next week to talk about linear algebra. Because this situation, this linear system of ODEs, can be rewritten in a matrix form. So we're going to spend some time talking about matrices next week.